Jai Hind students, I am back with this topic of current electricity, and today we are going to discuss a very important topic, and that is Ohm's law. Actually, this entire unit of current electricity is based on this basic law in electricity, that is Ohm's law. The foundation of this chapter is based on this law, right? Now, before we discuss Ohm's law, we need to be aware of a term which is known as potential difference. In my previous lecture, we have discussed about a sort of electric pressure which enables charge to move or to flow inside a conductor in a particular direction. And students, that electric pressure is known as potential difference. I provided you with an analogy, isn't it? We are aware of water current. Flowing water produces water current in river, isn't it? Similarly, flowing charge produces electric current in a conductor. And in order for water or fluid to flow, pressure difference is required. In order for heat to flow, temperature difference is required. Similarly, in order for the current to flow through a conductor, the potential difference is required, right? So suppose this is a very simple circuit. Let us consider this to be a circuit which comprises of a bulb and a battery like this, right? And this is a key, suppose, which is a closed one, and this is a cell. Combination of cell, I have told you, it's known as a battery. Cell stores chemical energy, right? And it can be converted into electrical energy. It is composed of two electrodes. One is the anode and the other one is the cathode. That is, it comprises of a positive terminal and a negative terminal. So what happens is, some amount of work is done by the source, by the cell, in driving the charge to move in a particular direction and to complete the circuit. So that current is constituted in the circuit. Now, electric circuit, we all are aware, it's a continuous closed path of electric current. Now, current will flow from positive terminal to negative terminal. This is the direction of the conventional current. But in order for the flow of conventional current, the electrons must flow in a particular direction. And the direction of the electronic current is from negative terminal to positive terminal. This is the direction of the electronic current. This is the direction of the electronic current, that is the electrons. So this is a source which provides a sort of electric pressure which is known as potential difference. So this source performs some work in enabling the electrons to move from one end of the conductor to the other end so as to complete the circuit, right? So potential difference actually is, without potential difference, the charge inside the conductor won't flow in a particular direction. So potential difference actually is the work done per unit charge. Here the charge, they are the free electrons which are the charge carriers. So look students, potential difference between any 2 points, suppose these are the 2 points I am talking about. Potential difference between these 2 points may be defined as work done per unit charge in moving this charge from one point to another point. That is potential difference, right? And who performs this work? The source. The source performs some work in driving the charge so as to enable it to move from one point to another point so as to complete the circuit. So that work done by the source per unit charge from one point to another point or between any two given points is known as potential difference. So only under the influence of this potential difference that the charge can move in a particular direction inside a conductor, right? So potential difference is represented by capital letter V. This is potential difference. Work done is W, charge is Q, right? So its SI unit is volt. Work done, its SI unit is joule. And charge, its SI unit is coulomb. So, when the potential difference across any 2 points can be said to be 1 volt, the potential difference between any 2 points is said to be 1 volt when 1 joule of work is required to be done in moving a charge of 1 coulomb between the two given points in an electric circuit. Clear, students? So SI unit of potential difference is volt, right? So this is how potential difference can be defined. So work done is equal to potential difference multiplied by charge. This is another important relationship. This we can conclude from the theoretical definition of potential difference, right? So again, I must recap this particular topic. It's very, very important. Students, just remember this topic of potential difference with the help of analogy which I have just now explained, right? It's entirely due to the pressure difference that fluid flows from one place to another place. It flows from higher pressure to the region of lower pressure. And it's entirely due to the potential difference that charge will flow. And charge, I am talking about negative charge, so it will flow from lower potential to higher potential. So potential difference is actually defined as work done per unit charge in moving that charge between the 2 points in an electric circuit, right? Its SI unit is volt. Potential difference between any 2 points in a circuit is said to be 1 volt if 1 joule of work is required to be done in moving a charge of 1 coulomb between the two given points. That is how potential difference of 1 volt may be defined, right? So the cells or the battery or any other source that stores chemical energy inside it, and it provides the two terminals of the cell or the battery, it provides the electric pressure, which is actually potential difference. And this is this potential difference that enables the charge inside the conductor to drift in a particular direction. And that is when the current is said to be constituted in an electric circuit, right? So, let's now start with Ohm's law. As I've stated, it's a very, very basic law. So, Ohm's law, as I've stated, it is a basic law in current electricity. It is a basic law in current electricity. And before the statement of this law, you need to understand that this law is applicable only when physical conditions remain constant. Physical conditions like temperature, mechanical strain of the conductor, these are the factors which must remain constant. It is only then that Ohm's law is applicable. So, its applicability or its validity is only when physical conditions remain same. Physical conditions must remain same. Must remain constant. So, it is only when the physical conditions like temperature, mechanical strain remain constant, then only Ohm's law is valid. Now, let's consider a simple analogy. Suppose this is a conductor and ammeter is connected. Ammeter will discuss. It's a device which is used to measure electric current in a circuit, right? And this is a source. This is suppose 1.5 volt. This is the potential difference across the ends, right? This is a connecting wire offering some sort of resistance, that also we'll discuss. So it will certainly give some reading. Say the reading of the current is suppose 2 ampere, right? Let us assume it. Suppose this electric device which is used to measure current known as ammeter reads a current of 2 ampere in this case, when a potential difference of 1.5 volt is applied across the ends of the conductor, right? Now what happens is, when two cells are connected in a particular order so that it becomes 3 volt, two cells are connected in a particular sequential order in series so that now the potential difference becomes 3 volt. Now obviously the ammeter will also show some more reading. So in this case the reading of the ammeter would be 4 ampere. If the potential difference is made twice, the current will, through the circuit will also become 2 times. If another identical cell is connected in series, then the current will become 3 times as that of the original one. So what I mean to say is that as the potential difference across the ends of the conductor is increased, the current flowing through that section of the conductor also increases accordingly. So this forms the basis of Ohm's law. So now we can deal with the statement of Ohm's law. So, what will be the statement of Ohm's law? Physical conditions like temperature, mechanical strain remaining constant, the current flowing through a conductor is directly proportional to the potential difference applied across its ends. These are the ends. So as the potential difference across the ends of the conductor is increased, the current flowing through the conductor will also increase accordingly in proportion. Right? So again I repeat, physical conditions remaining constant, current flowing through a conductor is directly proportional to the potential difference. It is directly proportional to the potential difference. Right? So mathematically what we can say is, potential difference we are aware it's represented by V, current it's represented by I. So potential drop across any section of a conductor would be directly proportional to the current flowing through it. Right? That is also a statement. So you are aware, in order to eliminate this proportionality sign, we need to introduce some constant, and that constant is, student, R. Or it can be represented as V equals to IR. R is constant of proportionality, which is known as the resistance offered by the conductor. And this is the mathematical form of Ohm's law. So again, let us revise this statement of Ohm's law. Ohm's law, student, is valid only when the physical conditions like temperature, pressure or mechanical strain remain constant. If the temperature varies, then these two quantities will not be linearly dependent on one another. Right? The variation would not be linear. So Ohm's law is valid only when the physical conditions remain constant. So under similar physical conditions, the current flowing through a conductor is directly proportional to the potential difference applied across the ends of the conductor. So that's the statement of Ohm's law. So mathematically, V is proportional to I. So in order to eliminate this proportion sign, we need to introduce some constant, and this constant is represented by capital letter R. It's constant of proportionality. It is known as the resistance of the conductor. So V equals to IR. So this is the mathematical statement of Ohm's law. V is equal to IR. V is the potential difference applied across the ends of the conductor. I is the current flowing through the conductor. R is the resistance offered by the conductor. Right? So that's Ohm's law. So this is over. Now we'll discuss about this particular term, resistance. So in order to discuss this term, we will deal with this term both qualitatively as well as quantitatively. So let's first discuss it mathematically, right? So we'll discuss this term in detail, resistance. So mathematically, resistance is V by I, isn't it? This is the statement. So it can be easily defined. The resistance offered by a conductor is defined as the ratio of the potential difference to the current flowing through the conductor. Right? Again I repeat, resistance offered by a conductor is defined as the ratio of the potential difference applied across the ends of the conductor to the current flowing through the conductor. Now look, its SI unit is 1 volt. Its SI unit is ampere. So 1 volt divided by 1 ampere is 1 ohm. Ohm is the SI unit of resistance. It is represented like this. This is the symbol for writing ohm. This is volt, represented by capital letter V, ampere. Right? So SI unit of resistance is ohm. When the resistance offered by a conductor is said to be 1 ohm, the resistance offered by a conductor is said to be 1 ohm when a current of 1 ampere flows through it if The ends of the conductor are maintained at a potential difference of 1 volt. Right? So suppose this is a conductor. These are the two ends. Suppose the ends are maintained at a potential difference of 1 volt and a current of 1 ampere is flowing through it. Then the resistance offered by this section of the conductor will be said to be 1 ohm. So this is how the SI unit of resistance may be defined. Right? Now let's discuss resistance qualitatively. Qualitative study. Now students, resistance. It consists of the term resist. Resist means to oppose, isn't it? To obstruct, to provide some sort of hindrance, right? To provide some sort of hurdle. So I'll explain it. Suppose this is the conductor and potential difference is applied across it. This is the source or cell and potential difference V is applied over it. The direction of the conventional current is from higher potential to lower potential, while the electrons will drift along this direction in a direction opposite to that of the electric field. These are the positive ions. As I stated earlier, they are immobile. They are immobile, that is, they can't move, they only oscillate about its mean position. They don't act as charge carriers. They simply keep vibrating about its mean position. These are the electrons. Which electrons? Free electrons or valence electrons, which moves in a particular direction under the influence of this external source. So now they will tend to drift in a particular direction. And what is the direction of their drift? From lower potential to higher potential. Electrons being negatively charged will get repelled from this negative terminal of the battery. So they will tend to drift in a particular direction. And it is only when the charge inside the conductor drifts or moves in a particular direction that it constitutes electric current. And what is making the charge to move in a particular direction? It is the potential difference. It is that electric pressure which is known as potential difference. Work is being performed by this source. Right? Now look, as I stated, these are positive ions. These are positive ions. They are immobile. They are immobile. They don't act as charge carriers. Electrons only act as charge carriers. So what happens is, positive ions keeps on oscillating like this. They keep on oscillating about the mean position. So under the influence of this source, when the electrons drift in a particular direction, so what happens is, the electrons, they very often collide against each other and also with the vibrating ions. So as the electron collide with the vibrating ion, their motion get hindered, their motion get obstructed. This hindrance or this opposition or this obstruction offered by the positive ion of the conductor towards the movement of free electrons is known as resistance. Right? Students, there are a large number of free electrons inside a conductor. There are about, in a good conductor like copper, silver, there are about 10 raised to the power 28 electrons per meter cube. In 1 meter cube, there are about 10 raised to the power 28 electrons, which is huge. So, as they drift in a particular direction, the electrons very often collide against each other. And also they suffer collision against the vibrating ions. Electrons are drifting in a particular direction and ions, they are oscillating about its mean position. So the electrons, while drifting in a particular direction, they very often collide against the vibrating ions. And when they suffer collision, naturally their motion get hindered, their motion get opposed, their motion get restricted or hindered. Students, this opposition, hindrance or obstruction offered by the positive ions of the conductor towards the movement of free electrons is known as resistance. Right? So that's the qualitative study of resistance. Resistance itself, it denotes opposition, some sort of hurdle. Right? So this is how resistance actually may be defined. Now, since we have discussed Resistance. Now let's discuss the factors on which the resistance depends. Factors on which resistance depends, right? It depends upon various factors. It depends upon physical conditions. I have told you, if the physical conditions like temperature, mechanical strain remain constant, then resistance will also be constant, right? But in case temperature changes, its dimensions changes, then the resistance offered by the conductor will also change, right? So, factors on which resistance depends. It depends upon the dimensions of the conductor. Factors on which resistance depends. First is, it depends upon the dimensions of the conductor. It depends upon the dimensions of the conductor. Now, dimensions means I am talking about the cross-section area and the length. This is the cross-section area and this is the length. So, first and foremost, resistance is directly proportional to the length of the conductor. More the length of the conductor, greater will be the resistance offered by it. It's a simple analogy. Consider a conductor of shorter length and consider another conductor of longer length, of the same cross-section area, and let the same potential difference be applied. Now electrons will tend to drift in a particular direction. So in which case electrons need to follow or move to a great path, a larger path. Obviously, the conductor having larger length, in that case electrons will have to traverse larger distance. So the probability of electrons getting collision with the vibrating ions, obviously in that case will be much more. More the collision suffered, more the hindrance offered to the moving electrons, more will be the resistance offered by the conductor. So it is but natural that greater the length of the conductor, more will be the resistance offered by it. So students, this is the important point. Resistance offered by a conductor is directly proportional to its length. Right? Second, it is inversely proportional to the cross-sectional area of the conductor. Now look, this is the cross-sectional area, this is the cross-sectional area. Now, greater the cross-sectional area, more will be the charge crossing per unit time. And more the charge crosses per unit time, greater will be the value of current. And larger the value of current flowing in the conductor means lesser is the resistance offered by the conductor. So therefore, resistance is inversely proportional to the cross-section area of the conductor. What I mean to say is that thick wires offer less resistance. Thin wires offers large resistance to the flow of wire. So smaller the area, greater will be the resistance offered. Larger the cross-section area of the conductor, thicker the wire, lesser will be the resistance offered by the conductor. So, resistance of a conductor depends upon length and its cross-sectional area. It is directly proportional to the length of the conductor and it is inversely proportional to the cross-sectional area of the conductor. Right? It also depends upon the nature of the material of the conductor. Nature of material means the conductor must be made up of some material, whether it is made up of copper, it is made up of silver, it is made up of wood, it is made up of plastic. So, resistance does depend upon the nature of material of the substance. So, it depends upon the nature of the material. Third, it depends upon the temperature. That's a very, very important concept. This topic we'll discuss it in detail. But for the time being, you can remember, with the increase in the temperature, the resistance offered by the conductor also increases. I repeat, resistance of a conductor increases with the increase in the temperature. Right? So it does depend upon temperature as well. We'll discuss all these factors one by one. So what to do is, let's start with the mathematical treatment first. So combining these two statements, we can write it like R is proportional to L by T. Since R R is proportional to the length of the conductor. Also, R is inversely proportional to the cross-sectional area. Therefore, combining these two, we can write R is proportional to L by A. Again, students, this is the proportionality sign. In order to eliminate this proportionality sign, we need to introduce some constant. Here, the constant is rho. This is known as rho. It's like this. L by A. Rho is constant. This rho is known as resistivity. It is known as resistivity. Or it is also known as specific resistance. It is also known as specific resistance. This quantity, it depends only and only upon the nature of material of the conductor and is independent of the dimensions of the conductor. Whether you cut a conductor into several pieces, each piece will have the same resistivity as that of the original one. So always do remember, students, resistivity do not depend upon the dimensions of the conductor. It only and only depends on two factors. It depends on the nature of material of the conductor and it depends upon the temperature. With the increase in the temperature, the resistivity or specific resistance also increases. Right? And it depends upon the nature of material of the conductor. For good conductors, the resistance must be small, therefore the resistivity must also be small. So for good conductors like silver, copper, the resistivity is very, very small. Of the order of 10 is to a minus 8, 10 is to a minus 6. Right? And for insulators, the resistivity is large. For example, for wood, for plastic, it is of the order of 10 is to 14, 10 is to 16. And for semiconductors, the value of resistivity lies in between that of conductors and insulators. So, let's try to discuss this term, resistivity. Let's discuss this term, resistivity. So, what to do is, as I stated, it is a term which indicates the characteristic of the material of a substance, right? It indicates the behavior of a substance towards electricity. So it characterizes the electrical behavior, right? So mathematically, how do you define it? Let L equals to 1 unit and A equals to 1 unit. In SI, it would be 1 meter and in SI area would be 1 meter square. Then if it is 1, it is 1, then rho would be equal to R. Isn't it? So, using this mathematical concept, we can define resistivity. Now look, students, how to define resistivity? Resistivity or specific resistance of the material of a conductor may be defined as the resistance offered by a conductor having unit length and having unit cross-sectional area. Right? Resistivity or specific resistance is numerically equal to the resistance offered by a conductor of unit length and having unit cross-sectional area. Or it can be defined in some other alternative manner as well. I'll explain it. Suppose we consider a cube. This is a cube, suppose, of dimensions 1 unit. Suppose it's a cube of dimensions 1 unit. Right? This is a cube. So this will be its cross-sectional area and its dimensions is 1 unit. So what will be the cross-sectional area of this cube? It is 1 meter square. What will be the length of this conductor in the form of cube? It is also 1 meter. So it is satisfying these two conditions. So now you can define resistivity in terms of this cube as well. So resistivity or specific resistance is numerically equal to the resistance offered by a cube of unit dimension. Right? Resistivity may be defined as the resistance offered by a cube of unit dimension. So this is another alternative method. So let's discuss its SI unit now. So resistivity is RA by L. Simply, so the formula for resistivity is rho equals to RA by L. So what we can do is SI unit of resistivity would be, SI unit of resistance is ohm, SI unit of area is meter square, and SI unit of length is meter. So what you get is SI unit of resistivity is ohm meter. Ohm meter. So this is the SI unit of resistivity, which is ohm meter. So student, here I must repeat some important facts regarding the resistance and resistivity. Look, resistance, it depends on length, it depends on area, cross-sectional area, like this. It is inversely proportional to the cross-sectional area. And it depends upon the nature of the material of the substance. It also depends upon temperature. Right? This is resistance. While resistivity, it depends only on nature and temperature. Nature of the substance, nature of the material of the body. Right? So what I mean to say is that, suppose this is a conductor and it is cut into 3 equal parts. Like this. It is cut into 3 equal parts. Suppose its length is L. Its cross-sectional area is A. So this is A and this will be L by 3. It is cut into 3 equal parts. Suppose the resistance of the original conductor is capital R. So area remaining constant, if A is constant, then resistance is directly proportional to length, isn't it? So here length of each section becomes 1/3 of the original length. So its new resistance would be R by 3. So if the length decreases to 1/3, the resistance offered by the conductor will also decrease to 1/3. Right? But students, the important point is that resistivity. Suppose it is made up of copper. This part, 1/3 part of the original one, it is also of copper only. So resistivity won't change. It will remain constant. Because formula is rho is equal to R A by L. A is constant, right? If the length is decreased 1/3, resistance is also decreased by 1/3. So the ratio R by L always remain constant. On changing the dimensions, the resistance also change, so that this entire term always remains constant. So that is what the most important fact is. Resistivity of a conductor does depend only upon the nature of material of the conductor. It is independent of the dimensions of the conductor. And obviously, we'll discuss it in the next lecture. It also depends upon the temperature. Now look students, with the increase in the temperature, what happens is, the positive ions, it starts vibrating more vigorously and with greater amplitude. So the electrons, the probability of electrons colliding with the positive ion increases. That is, collision takes place more frequently. More collisions are taking place. So obviously, more is the hindrance, more is the obstruction. So more is the resistance or more is the resistivity. So always remember, resistivity increases with the increase in the temperature of the conductor. So if the resistivity increases with the increase in temperature of the conductor, so will the resistance will also increase with the increase in the temperature, right? So we will discuss other topics in the next lecture, right? Till then, please do revise all the topics. In this lecture, we have discussed Ohm's law, resistance, factors on which resistance depends, and resistivity, along with their mathematical as well as their qualitative study, right? Do revise these topics and we'll continue in the next lecture then. Do take care.